This is example on atmospheric standard pressure. So we're gonna have certain dimensions, heights in which the airplane is flying, and you're required to find the pressure, temperature, and densities. Let's go with the example. So in this particular example, you got two aircrafts. One is flying as subsonic, the other is flying supersonic. And just by the problem itself, we know that everything flying around 11 to 10 kilometers, that's going to be a subsonic aircraft. So for the subsonic aircraft, you know that you're flying at altitude 13 kilometers. Typically, that's not true. This is just notional for this particular example. And you're asked to find your density and you're asked to find your pressure. We can also find the temperature as well, and we will do that, but that's not asking the problem. Then he's saying they have another plane that's flying over here, and he's flying at an altitude of 20 kilometers. And we also asked to find the density, asked to find the pressure. Now, note that anything that's flying very top high, that has to be a supersonic aircraft. Okay, so that's going to be supersonic. So the problem itself, basically, we can see all the layers, atmospheric layers, but we are mainly interested in a value that's over here and a value that's over here. Those are the two values that we are really interested in knowing. And these are the constants, the air constants. Those are given to you. Those are functions of air. And we know that. We know the value. And it is meters, okay? It's intentional. It has to be meters. So we know this. This is what your table actually looks like. Just to understand that you have the standard atmosphere. We want to know all the altitudes. And from here, we want to find all the variation of pressure, density, and temperature. And that's what we are really looking for in this particular problem. So let's go ahead and review some of the some of the equations that we had. Um, just give me a sec. So some of the equations that we have. So anytime I'm going from this point to this point, these are the equations I'm going to use. This is for varying temperature. This is isothermal case. So these equations are valid all the way across here to there. These are valid there. And then what I want to do in the first part, note that my problem is really asking me to find your temperature at these locations. Don't forget this, I'm asked for to find the temperatures in these locations. So either I can go to that table and find this value and then go from here to here, or go from here to here. The tables also have those values, and the one we calculate should be close enough. However, the approach that we're going to use, we're going to go from here, just for practice purposes, we're going to find what is the properties here, and then those properties will serve as the input for here, and then for the second location of my aircraft. So to do that, we know that we have to go to point 1. We have to go to point 1 to point 2. Okay, so this is sea level. Let me change my marker. This value is nothing else than sea level. Okay, and these are the properties at sea level. So the ones that we want to find now are at point 2. Then once we have that, okay, those values, value 2 now becomes the value 1 and will be the input value for my next iteration, for next position that I am, that I want to look for. So it basically becomes 1 and 2, and then next time it become 1 and 2 up here. That's what we are basically trying to do. And these are the equations for that. So we're going to come here in this problem. So We want to go from 1.1 to 0.2. So that's the problem we want to do. Okay, so let's go ahead and do that. To do that, so now we're going to have, let's separate these values. You may pause and take notes if you want to. So the values here, and the value here is 1.225. This is the density. And my temperature 1 is 288,150. And my final temperature here will be 216.65. So we know those temperatures. Everything to the power of this is 9.81. Gas constant is 871 multiplied by minus 0.0065 plus 1. Okay. And just remember, I just mentioned that before, that your gas for this slope here is A is equal to minus 0.0065 Kelvin over meters. You don't have to convert this in kilometers. Okay, so if I solve for this density now at 11, you're going to see that you get a density of 3.6363, 10 to the minus 1, and it has unit of kilogram meter cube. Now we can go here. I'm sorry, this is all to the power. Okay, and then here, now we use the pressure is 1.0133 times 10 to the plus 5. And the same temperatures. This is my final temperature. This is my initial temperature. Minus 9.81 divided by 287 multiplied by what goes in here is minus 0.0065 plus 1. And if I find this pressure, it gives me 2.265 10 to the 4, and we can call this pascals. Okay, so that is the pressure, the pressure at 0.2. These are the input values at that location right here. And just as a comparison purposes, if you go here and you see these values, we can see that we were very close to each other. You see, I got 2.26, 2.26, and for the density we got 3.63, 63. It's never going to be exact, but this is, and it's never going to be exact. Okay, this is all approximations. And so these values are the ones that we will use for our further calculations. Okay, so with that said and done, we know these values, we know the input values, those become the value of, that becomes my temperature 1, temperature 2, and my rho 1 and rho 2. Okay, so given that, now I want to find what happens here. This is at 13 kilometers. This is what I want all my pressure and temperatures. So at 14 kilometers, my equations are, so these are the equations for this segment, this section, for my pressure and my density. So as I apply all my equations here, now my rho again becomes the rho for this value. And from the previous slide, we found that this was 0.36363 times 10 to the minus 1. And that is rho. E to the G is 9.81. Now I have to multiply this by 1,000 because this is all in so the units can all make sense, but this is in kilometers, so I have to convert that in kilometers. And the temperature at that location was 216.65. Okay, and multiplied by your delta, it is 13 minus 11. Okay, so your rho at 13 will be 2.6523, 10 to the minus 1 kilograms over a meter cube. And your pressure, that will be P1, the location here, and your starting pressure there is 2.265, 10 to the 4, and 4. And then this is e to the minus 9.81 times 1,000. 287 multiplied by 216.65, and delta 13 minus 11, and the value that I get for the pressure is 1.6495, 10 to the 4, let's just call this pascals. Okay, so if you go to the table, it's a good comparison. I'll just check what happens in the table. So at 13, so if I go to 13, you can see that at 13, I got 1.6495. And for density, I got 2.6523. So we are very close to each other. It's a good checker. Sometimes we are close, sometimes we are not. Okay, so the next point that we are interested in is now my second point that's up here. So again, now we go to, I'm still going to use point number 1 right here. And this is going to be point number 2. And replace these values. Now the only thing that you can see that's going to change from previous slide is my H2 and H1. Here, again, this is 3.6363, 10 to the minus 1. E to the 9.81, you have to multiply by 1,000 here. 287 times the temperature is 216.65, and the delta is now this was at 20 minus 11. Remember, this is where this location was. This was at 20 kilometers. So the answer that you get for here, when you calculate this, 8.79, 10 to the minus 2 kilogram over meter cube. Then the pressure, again, is the same value that we start at this particular location, time 10 to the 4. E to the minus 9.81 times 1,000. Remember, this is just to convert this in kilometers, I'm sorry. 287 times 216.65, multiply 20 minus 11, and you get a value of 5.4668 times 10 to the 3 pascals. Okay, so this is the first part of the problem. The second part, the problem is asking you is, can you give the difference of the air density? The air density, so that would be the air density of supersonic divided by the air density of subsonic, and the values that you get for supersonic, for the case of subsonic, it was density was 2.26 2.6523 10 to the minus 1, and supersonic was 8.79 times 10 to the minus 2, and that gives you a value of 0.334. So you're saying roughly that your supersonic aircraft is flying at the density of approximately half the air density, a third of the air density of your subsonic aircraft. This is actually typically very true. It is about a third. So this concludes example on atmospheric pressure.